So let's take a look at absolute value. This is sort of, I call it a hangover from working with numbers. When we work with numbers, we're never responsible for putting the plus sign in front of a number because we assume it's positive. When we put the dash in front of a number, we know it's the opposite of a positive number. We call it negative. And when I used to teach 095, I used to have a black and white tile in my hand. One side was black, one side was white. And I'd say, okay, the black side is positive, the white side is negative. I'm holding the tile in my hand. What kind of number is it? And the students would look at me like, what do you mean? How do we know? We can't see it. And that's what you have to realize when you see X. When you see X, you have no idea what kind of number it is. But our training with numbers for all those years before we got to algebra, when you see X, what kind of number do you see, really, truly? You see a positive number. That's what you have to undo, okay? So when I write a statement like this, the reason why this statement is false is it says no matter, it's for any real number, so no matter what number you put in for X, the answer comes out looking just like it did when it went in. That is not true for absolute value. Absolute value says no matter what number you put inside, it comes out being positive. So if you put in a positive 3, guess what? It comes out looking just like it did when it went in. Okay? So here's, I'm just going to use colors here so you can see this. Comes out being identical. If you put in a negative 3, it does not come out looking exactly like it did when it went in. How does it come out? How would you write the answer here without writing 3? How could you say what the answer is without writing the number 3? How does it come out? What is the relationship between negative 3 and 3? What's the relationship between those two numbers? What are they? 3 and negative 3. No, in relationship to each other. 3 and negative 3. What do you call them? If we were multiplying x minus 3 times x plus 3. Real simple question. Don't overthink it. 3 and negative 3. What kind of numbers are those? Opposites, right. So it doesn't, the answer here, we know the answer is the positive number 3, right? But when it comes out of here, it doesn't look exactly the same. It's the opposite of how it looked, right? So when you say this, it comes out like this. It's the opposite of how it looked when it went in, all right? So we simplified this and call this 3. So note, it goes in as negative 3, it comes out as the opposite. That's true for all negative real numbers. If I have in here negative square root of 7, it doesn't matter that it's irrational, it comes out the opposite, positive square root of 7. So you can't satisfy this equation with one statement for absolute value. We're going to see in about a week or so, oh actually, yeah, it's probably a week. We're going to look at this. When you write this statement, you have to divide it into 2 pieces. This is what we call a piecewise function once we get to functions. We can't just write one equation. We have to say, hey, there's 2 different cases here. I come out looking exactly like I did when I went in if I'm 0 or I'm a positive number. So you have to write 2 statements. You have to say this. So if you go in as a number from 0 all the way out to infinity, positive infinity, you come out looking exactly like you did when you went in. However, if you go into that jail and you're a negative number, unfortunately our incarceration system doesn't work like this. If you go in as a negative number, you come out as the opposite, because the opposite of a negative number is positive. So this is how you write the definition, and this should have been in your book, I think in the very first section. I know it was in your lecture notes in the very first section, that the absolute value of x is written in 2 parts. And if you look at the graph for the absolute value of x, if you graph this, it's actually the part of 2 straight lines. We don't have this part of the straight line. This straight line is y equals x. That's called the identity equation. Whatever x is, y is the same. Here's the other part of the absolute value. So we don't have this part graphed. This is y equals the opposite of x. So that's what the absolute value function looks like if you graph it. Because if you go in as 0, in fact, you could have this statement be x greater than 0 and x less than or equal to 0. 0 can go anywhere because 0, the absolute value of 0 is 0. It's its own opposite. It's the only number that is itself or its opposite. So you can see here, if you put in a positive 2, you come out looking exactly the same. If you put in a negative 2, you come out being the opposite. You don't come out being the same. Okay. So when you're dealing with absolute value of x, you have two conditions that must be met, or you have two situations that you have to look at. Is that clear now for those of you who wrote true for, was this number 4 on the anticipation guide? Any questions on this? Okay, at the end of your class number 1 packet, I'd like you to turn to lecture notes number 1 right now. You have a little exercise that's called sometimes, always, never. Try those 3 questions by yourself and then compare it with your group. Here it is right here. The absolute value definition, and here's the sometimes, always, never questions. Try those. Take about 3 or 4 minutes. Put your flag up when everybody at your group agrees, and then we'll come back. All right. Okay, so let's see. Table 1, what did you get for the first one?
I said sometimes.
You said sometimes. Oh. Right. So if you answer sometimes or never true, either change the statement so that it is always true or show a counterexample. What's an example of a counterexample? A counterexample for this would be this. Here's a situation where x could be a number and your answer is not negative. It has no sign. So that's why sometimes is the appropriate answer here. Okay. Table 2, what you say for the next one? It's never. Do we have agreement on that? That when you come out, it doesn't matter how many little dashes I put inside those, inside the absolute value. Whenever you come out, no matter what you look like when you went in, your answer is always positive. Okay? And then the last one, table 3, Eileen, Jim, and Isabel? Always. Because what this does, a subtraction of 2 numbers always has the same distance between them, no matter what order you subtract. So when you subtract, you know change in the order of subtraction changes your answer. One order is either positive and one is either negative. But once you place these absolute values around it, you're saying, I'm not interested in the sign, I'm interested in the distance. And the distance between the same 2 numbers is always equal. Because that's the meaning of absolute value. It's the distance from 0. All right, so I hope that clears up some stuff about absolute value. So now we come to Petru's question, which is a little more involved. And I think if you had Sandy Goki for 095, she covers this. And other teachers may or may not, because they're just trying to get you through 096 with as little headache as possible. So, for example, when you have this statement, can you get that door for me, Dale? When you have this statement, your 096 teacher may allow you to write X and give you a check. But if you read the directions for any work that you did like this, either as a group activity in 096, because I wrote the lecture notes for 096, so I know what they say, all those lecture notes you used, okay? It says assume X is greater than or equal to 0, or it says assume X is positive. So there's always an assumption. It should say assume X is non-negative. When we say non-negative, that means 0 or to the right of 0. So on a number line, non-negative means this. Solid dot at 0, and then you color everything in to the right. So if you assume X, this little thing here, is a 0 or a positive number, it comes out looking These two things, squaring and square root, are inverse operations. They undo each other. You come out looking exactly the same. However, now that you've graduated and you're in Math 107, we don't make those assumptions anymore. The number that can be in there that's being squared could be a positive number or a negative. But we know when we undo a squaring by taking a square root, the answer has to come out to be positive. So that's what this symbol means. If you see this symbol all by itself, it's saying, I want the positive square root. If you want the negative square root, so this is called the principal square root, which means your answer is always positive, and this means the negative square root. Okay, just like we do with numbers. If we want the opposite of the positive thing, we put the dash out front. So here, your answer has to be this. Because if x is a negative 3, if I put a negative 3 in for x, it doesn't come out being negative 3, it comes out being positive 3. So the only way to ensure that your answer is positive is to put this thing around it. So you were sort of like let off the hook in 096 by being allowed to write this. So that's why in the homework, let's see, I'm going to work backwards from Petru's question. Here was the answer. This was the answer to one of the homework questions. And I want to go back to what my question started out as. Well, if 4 came out of the square root, if 4 came out, it must have been a 16 under the radical because the square root of 16 is 4. So I know that what goes underneath this radical had to be a 16. It already has a 5. And if the square root of, the absolute value of x came out, then it must have been this. So my original problem for my homework would have looked like this, 80x squared. And to do this problem, you take the square root of 80 times the square root of x squared. You divide it up into its two factors. Okay, language is really important because I use it every day. When you multiply each of the individual pieces, it's called factors. Square root of 80 times square root of x squared. When you write this now, you no longer write x. The square root of x squared is the absolute value of x. What's the square root of 80? Well, one of the things you got in 095 was you got a perfect squares and a perfect cube sheet. So I did that too. I put that together a long time ago for my students. And being familiar with these square roots is really important when you have to simplify radicals. So if I want to simplify this radical, if possible, I want to break it up so that the number under one of these radicals is a perfect square. So I come up here, well, 1 divides everything, so that's kind of useless. Does 4 go into 80? Yup, I could say square root of 4 times square root of 20, but I want to find my biggest number if possible. 9 doesn't go into 80. 16 goes into 85 times, so you go like this. I'm going to identify all my perfect squares with a blue color. So the square root of 16 is 4. The square root of x squared is the absolute value of x. And I'm left with poor old square root of 5 because that's irrational. You can't do anything with that. So Petru, that's why you have to have the absolute value. Why you didn't have to have it for number 22, I can't answer you. It should have had an absolute value around it.
This is my question.
Yes, I don't know why. I know. That's what I'm saying. I don't know why they didn't require you to do it. On 22, should have to put the absolute value there. So let's see. This might help you, Kyle, with how you put your answers in. So let's go to 22. Here's our question. Okay, use the product rule to simplify the following expression. Assume the variables, oh, here's why. They're letting you off the hook. That's why in number 22, you don't have to put absolute value of x because it says assume variables are non-negative. So you're assuming that x is a number from 0 all the way out to infinity. That's why you do not need the absolute value around x. In 21, I bet they don't have this statement in 21. Let's take a look at 21. Yep, See? It doesn't say assume your variables are non-negative. That's the difference between 21 and 22. You're welcome. Okay. So that takes care of Petru's question, and it takes care of several Eli's question, and someone else had this originally. So let's see where we go now. Anya's, okay. Prerequisite packet, we have a to the -4 over a to the, I think I copied this wrong, -5 times b to the 3rd over b to the 5. And this will also help you, JP, with multiplication of fractions. This is what we call a single fraction. Okay, this is a single fraction. That involves multiplication. So one possibility was my original multiplication problem of 2 fractions may have looked like this. That may have been my original problem right there. Okay? My original problem also could have been a to the -4 over b to the 5th times b to the 3rd over a to the -5. The order of these things doesn't matter, but for our purposes, we're going to keep the like bases in the same fraction. Okay? So your job is to simplify each of these. Okay? So I'm going to give you a little memory device. Okay? If this is going on YouTube, I don't care. Here's how you remember your operations for adding with like bases and subtracting with like. Can everybody remember MadSex? Yeah, I think so. Okay, what's that mean? When you multiply, you add exponents. When you divide, you subtract your exponents. Okay, so that's one way to remember the 2 of the properties. I have some other memory devices for the other properties of exponents, but you'll have to see me in the studio for that. Cancel? What do you mean cancel? Yep, but I'd have to write it all in factored form, top and bottom, to cancel. In other words, if I had something like this, Eli, with positive factors like that, sure. By canceling, I'm finding forms of 1 like that. That's my answer. Yep. But this, it's a little hard to do with this because I've got negative exponents. So we'd have to have both of these be turned into positive exponents in order to do that. But it's a little more complicated, yeah. So why do we have rules to mess up algebra, students? No. Rules are efficiency. That's it. That's all it is. Rules are to make your problem solving more efficient. Now, when you first learn exponents here at GCC, Sandy doesn't teach you any rules. She has you do it all out by hand the long way. When you get to 096, you get introduced to the rules. And the thing about exponents is you can do these problems several different ways. And I could spend the next 15 minutes telling you all the ways to do this one simple problem. I'm going to take the shortcut and use the rule. To simplify this problem, I'm dividing, so I think of my MadSex little acronym, and it says when I divide, I subtract my exponents. I don't worry about the fact that they're positive and negative because I know how to add and subtract positive and negative numbers. Okay, I can handle that because I'm in Math 107 now. So this becomes a to the -4 plus 5, which is a to the 1. So this becomes a to the 1 on top. I don't have to put in the 1. B to the 3rd over B to the 5th. You can already see you have more in the bottom than you have in the top, so you have a deficit if you want to think of it that way. You have B to the 3 take away 5, which is B to the -2. A negative exponent just tells you have 2 factors of B in the denominator. So if you wrote this out as 2 separate fractions, JP, and it's not just JP, many of you have this question, you would write it like this. A times 1 over B squared. And remember, A is really sitting on top of the number 1. And when you multiply, you don't have to have things look like, only in adding and subtracting. You just multiply straightforward. Numerator, numerator, denominator, denominator. And there's your answer as a single fraction. And this is how you would leave it on a test or a quiz or any kind of problem you're solving in Math 108 or Calculus, wherever you're going. Okay, yep, Emily? Yes, and I don't teach that because people do it when they're not supposed to do it. In other words, yes, if you could explain to me why that happens, and you've shown it to yourself and you really get it, then I would say, I mean, I can't control what you do, but this really says this, and this really says this. That's what a to the negative 4 and a to the negative 5 means. And now we're going to answer JP's other question. Here I have a division of fractions problem. Anytime you divide, it doesn't even have to be a fraction. It can be whole numbers. This is always true. Any division problem is changed to its inverse operation, which is multiplication. And when you divide by any number, fraction or otherwise, it becomes the reciprocal. So the numerator stays the same, and now this is what you get. And notice your answer is a to the 5th over a to the 4th. So what Emily's trying to show you is if you did enough of these for yourself and you found the pattern that, hey, in the end, this negative 5, because this is a fraction in the bottom, like 1 over a to the 5th, that's going to be inverted, and that will go to the top as positive. And this negative exponent will stay in the denominator. If you understand that, then sure, go ahead and flip it and change positions and all that. So some people teach this as position. When you have a fraction, if you have a negative exponent in the bottom, you change the position of that exponent by creating a positive 5 in the numerator because you've changed its position. If you have a negative exponent in the numerator, you can change its position and make it a positive exponent, but you have to change the position and put it in the denominator. But what happens is, I've tried teaching it this way sometimes, and students start switching things even when they don't have to. And I want to give you an example of what a student who doesn't really understand why that works might do. I'm not saying you would do this. So here's a problem. If you subtract the exponents, you can't go wrong. 3 take away a negative 5 is a to the 8th. So that's your answer. Okay. But you've seen this trick somewhere, right? You think of it as a trick. Oh, I can move stuff around by changing the sign. So I've seen students do this. Oh, no. They do this. They put this on top and that down bottom. Well, that can't go down bottom and keep the same sign. So you see, you start when you don't understand why something works, and this is part of our problem with math education, is that you were taught things rotely and you just followed things. Maybe not totally understanding it, not your fault, because maybe your teacher never really fully explained it to you or understood themselves where it all came from. I'm talking way back as youngsters, okay? So there's a little danger in that rule, and Emily, I've seen you use it correctly in the studio, so you might be okay. So if you were using this rule, you don't have to touch this. It's already happy. It's positive. This is the only one that's unhappy. To make a to the negative 5th a happy exponent, you change its position by moving it to the numerator, and when you move it, you must change its sign. There's your a to the 8th, exactly the same answer as if you subtract. I'm just going to caution you, just be careful if you want to use tricks that you really understand why you're doing them. And the best way to really understand them, and I know I'm being crazy, but is for you to make up a whole bunch of problems yourself. I don't care what they look like. They can almost look like identical problems like this. These almost look the same, right? I'm just changing the sign. Do 3 or 4 of these where your problem almost looks the same, but you're just playing around with the positive and negative. Use your rule and then try this movement positional thing and make sure you come up with the same answer. When you feel confident with it, then you'll feel free to use that. Okay. Unfortunately, the question about can I go review exponents, I can't. That's what the book does. Okay, that's what your second packet does, and that's why I'm in the math lab. This is a prerequisite knowledge, so I can't take a whole lot of time to do this. I'll be glad to review this, Agnes, with you in the studio right after class. Sure. Mm-hmm. Oh, that's different. What? No, wait. What's your original problem look like?
Well, the same one.
Oh. Oh, okay. Hang on. Okay, so the same exact problem. What, a to the fourth you want?
Sure.
Over a to the negative 5 and b to the third over b to the fifth. Okay, you guys work that out at your seats. See what you get there. Where? Oh, well, this is a totally different. Never mind. Don't work this out at your seats.
Yeah.
Oh, so a plus in between. Okay. All right. Totally different problem. And the plus on the bottom too? Okay. Okay. You can't do anything with that. Multiplication rules for exponents. What are exponents? Repeated factors. Factors, 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 folks. I know I get silly when I do this. Addition. This is terms. What you do with adding and subtracting in math and what you do with multiplication and division, two totally different worlds. Totally different worlds. There's nothing you can do with this. This is, in other words, what two fractions would I had to have added to get this single fraction? This is a tough, it's not a tough question, it's really an arithmetic question in a lot of ways. Here's a single fraction. Now, a lot of you just finished Math 096 where you had to add algebraic fractions. What two fractions would I have had to add to get this one fraction? Now, I'm saying add. Why am I saying add? Because I'm just looking at the numerator and I've added two things. So what must one of the numerators look like in these single fractions? What would one of the numerators look like if I ended up with a to the fourth plus b cubed? A to the fourth. So I'd have one numerator that would look like this. And what would my other numerator look like? B to the fifth, b to the third. Okay, what must be true in all of math, starting way back in grade 2 and 3? If you add something, how do you add things? What must be true about them? They have to have the same denominator if you're dealing with fractions, or if you're dealing with any kind of addition and subtraction, they've got to look like. Like. That's what you have to remember. Fractions, we say same denominator. When we're adding terms like this, we can't add those because we say they're not like. When you were very young and you were told to add these two numbers, you did something. You learned a rule of algorithm. You lined these up so that the like place values lined up. You've always used this idea. So to add these two fractions, what must have been in each of these denominators? A to the fifth plus b to the fifth. That's the only way you could add these. Now, what do people who are unclear about the difference between multiplication rules with exponents and how to reduce a fraction, what does a person do who's all confused by all those rules? They start putting slashes through these things. Okay, you see the b cubed and the b fifth and you go like this. What you're forgetting is there has to be a big fat multiplication problem in between here in order to do that. You only reduce fractions by dividing out a factor of one. Factor, not addition. When you add one to something, you change it. So I'm trying to do like Math 090, Math 095, Math 096 in one question here. There's a lot in this one question. Does that help, Eli? Okay. All right, so where are we now? Let's go back to Jen. Jen noticed a typo in class 5, the worksheet for class 5. So go to the very end of class number 5. You'll see a group activity called modeling resistance. Okay, and it's what letter is it, Jen, at the end of 5? It's letter right here. It's number 3. Do you see number 3 has the same two equations side by side? That was probably just my attempt, or Caitlin's, I don't know which one of us did it, to make that equation look a little bigger, and we forgot to cut out the first equation. So there's a little typo there. You can cross out either the smaller equation or the larger equation. Class 5, number 3, you have two equations side by side. They're identical. Class 5, right here. Okay, has everybody found it? So just cross out one of the equations. Who's sitting here? I'll cross it out for them. All right. Class 4. Class. So this worksheet is an application of rational equations, which usually drives people crazy. Do you still need this to be done, Jen? Solve for R? No? Okay. Okay. So here we come with another exponent rule. It's amazing, isn't it, how you spend all this time doing exponents and radicals and stuff in 096. Some of you just had that class within the last month, and these things just bug you to no end, don't they? It's horrible trying to get these exponent things down. You're going to use two different rules here, exponent rules. You're going to use the idea that if you have a product is the result of a multiplication problem raised to a power, then this power becomes the exponent for each factor. Okay, so I know you're dying to know what acronym I came up for this, aren't you? Or don't you care? It's all right. So when I'm doing my little memory thing a couple years ago in 096, when I came up with mad sex, I'm like, what am I going to do with this? So most people say they spread the power, right? So I'm thinking, you know, I'm sort of a little bit of 60s kind of kid. I was young in the 60s, but I was around in the 60s. And of course, in the early 70s, I was in college. And, you know, those of you who know anything about history, it was a very sort of tumultuous time in the U.S., a lot of riots and lots of rights, you know, being fought for, Vietnam War, blah, blah, blah. All right. So there was a saying, power to the people. Okay, so I'm thinking, power to the people. How the heck? I got a power, I have no people. So then I came up with power to the multi-dudes. Oh, where's Kavanaugh going with this one? Okay, here's power to the multi-dudes. So this is some ways to help you remember your exponent property on this. So when you have a multiplication or a division problem, you have power to the multi. The power comes to the multiplication problem, and it comes to the division problem. So that's the best I could do for those two rules, power to the multi-dudes. All right, instead of power to the people. So this power is going to come down and attach itself because it's a multiplication problem. If there was an addition or subtraction there, you couldn't touch it. Nothing. Okay, as long as it's multiplication, you're okay. So this is to the 1/3, x to the 9 to the 1/3, and y to the 6 to the 1/3. And your final exponent rule is right here. You have a power raised to a power. When you have a power raised to a power, you multiply. And my little acronym for that is really too weird to tell you. You're not going to get it unless you're in class with me. Cubed root, that's what 1/3 means. A cubed root of 125 is 5. You multiply those, you get x to the 9/3 and y to the 6/3. So that's 5x cubed y squared. All right, Jen? Okay. All right, so let's see, what else do we have here? Petru, we've got this all done. That's where we started. And Josh. Josh wants us to go over 10, 14, and 15 of the anticipation guide, number 1. So let's take that out, that pink sheet. This is number 10. This is number 14. And this is number 15. Okay, so this covers a couple of areas in your, remember this anticipation guide was supposed to cover different areas in your classes 1 through 7. So this had to do with rational expressions and reducing them. This had to do with solving quadratic equations. And this has to do with multiplying complex number forms. Okay, so let's take a look at number 10. If you look at number 10 in your anticipation guide, the full question says, the expression, this is an expression because there's no equal sign with it. 5 is an expression. You can make it as simple or as complicated as you want. This is an algebraic expression. Simplifies means reduces to the consecutive integer that follows -4. I didn't have to say that follows. I could have just said the consecutive integer after -4 or whatever. But the wording here is a little confusing. Consecutive means add 1. So whenever you see consecutive integers, if you have a number line, -4, -3, -2, -1, 0, 1, 2, 3, consecutive integers is moving to the right by adding 1. So the next consecutive integer after -4 is -3. So what this question is asking is, does this reduce to -3? That's the question. And in order to reduce, you can't do anything right now because you see subtraction and addition here. You can't touch it. However, to reduce, you try to factor everything. The bottom can't be factored. It's already prime, so you leave that as it is. But the top can be factored. You can pull a -3 out of the top. And what you would have left is y plus 2. And you have a y plus 2 on bottom. And there's your big fat foo-foo right there. Fancy form of 1. So this is true. It does reduce to -3, which is the next consecutive integer from -4. Okay, 14, I could do a song and dance, as I always tell my students. And it really, doesn't matter because this is a hard thing to break. Again, when you see this x being squared, you have to train your mind that this is not just a positive number. So when you apply the square root principle to both sides of this, when you undo squaring by taking the square root of both sides, the problem, and again, I've tried teaching this in 096 and people just totally ignored me. They didn't want to do it. When you write this, you do not write x. The square root of x squared is an absolute value. This says the positive square root of 9. Now you can't go wrong. Once you see that, you know that what goes inside for x could be 3 inside that absolute value, or x could be -3. But trying to get you to insert this line is really like trying to pull your teeth. It's really hard. This guarantees that you don't get this question wrong. I cannot tell you how many papers over the last 30 years that I've given this question, how many students I've given this question to, and I've seen this answer only. I've had to take half credit off. Yes, if you can remember that. But most of you will forget it because you square root it. This is what you do. You square root it. You go like this. And this is what you write. And that's not correct because x could be -3 as well. So I did get up one time and did a little song and dance. No, I didn't. I'm just teasing. All right, so what's another way? Linda, please tell me something I can do so I don't have to do that absolute value. This is the way you can get your answer always without having to do the absolute value. Do what you always do. First of all, recognize it's quadratic. When it's quadratic, unless the number over here in this particular form, if it said x squared equals 0, then your only one answer is 0. But any other number in this form where you have x squared equals a constant, and that constant does not equal 0, you always will have, always, two answers. Now, if you're someone like Dale who can remember the properties like the books give you, your books go like this: x squared equals c, x equals plus or minus the square root of c. If you can remember those things, you're golden. Most of us can't. We kind of go back and we're fooled by seeing the x square and the x and only thinking positive. So what can you do? If you're just a regular old Math 107 student, you can say, okay, this is quadratic equation. To solve any quadratic equation, I set my equation equal to 0. The minute you do this, you now have two choices. 3a, you can factor it if it's easy to factor, or you can use your quadratic formula. Hopefully you recognize that as the difference between two perfect squares, which gives you two totally different factors. And that way you are setting yourself up beautifully for getting both answers. Because x plus 3 equals 0 when x is a negative 3, and x minus 3 equals 0 when x is a positive 3. You'll never go wrong, ever. And guess what? This number on the other side does not have to be a perfect square. It could be any number. For example, you could have this. Give me my arrow. Any number. It could be x squared equals 7. Doesn't matter. X squared minus 7 equals 0. What's the square root of 7? The square root of 7. X minus the square root of 7. And there's your two answers. X equals plus or minus the square root of 7. So don't feel like it always has to be a nice pretty number like 9 or 16 or 25. It works for any number. And if you don't feel comfortable with that, you can always use your quadratic formula right here. Once you set it equal to 0, you can always use your quadratic formula. And unfortunately, I don't know if you've listened to the lecture notes, but if you listen to mine, we sing the quadratic formula. To Pop Goes the Weasel, x equals negative b plus or minus the square root of b squared. Whoops, what am I doing? Is that b? What's b here? What's b? 0, right. A is 1, that's a coefficient here. Our middle term, if we put it in, would be 0x minus 7. So A is 1, B is 0, C is negative 7. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Here it goes. Let's so you never forget it. X equals 0 plus or minus the square root of positive 28 all over 2. The 0 doesn't do anything. You have plus or minus the square root of 28 all over 2, and here's where you get simplifying your radical. You go back to your perfect square sheet, 1, 4, 9, 16, 25. 4 goes into 28, so this is plus or minus the square root of 4 times the square root of 7 all over 2. That's 2 square roots of 7 all over 2, plus or minus x equals plus or minus 7. Now, I don't know about you. I would certainly rather factor that and get plus or minus the square root of 7 than do all of that. Okay, so my job is to show you as many different approaches as possible to problems. But again, if you have an equation, a quadratic equation with a square on one side and a number on the other side, your answer is plus or minus the square root of this number. Now, what happens if you have something in front of it like this? What do you do first? By what? Right. You want to isolate your x squared term, so you get x squared equals 6. So the answer here is plus or minus the square root of 6. And it doesn't change if the stuff in parentheses isn't a baby x, but it's something like this. I'm just making something up. See this as something squared. Forget the fact that it's x minus 2. When you take the square root of this side, you're going to get x minus 2 in absolute values, but you can do this. You can avoid that by simply saying this. Just like if there was a big fat x here, x squared is 21, you'd say x is plus or minus the square root of 21. Drop your parentheses. Add 2 to both sides. So that looks a little bit now like the answer for a quadratic equation, right? 2 plus the square root of 21, 2 minus the square root of 21. So you had, these are the things I think you had in section 1.5. Am I correct? If you've gotten that far? Okay, I know some of you haven't. Okay, Emily, simplify this. Why don't, now that we've gone over all those exponent rules, power to the people, power to multiplication and division, mad sex and all that, you all try this at your seats. I've been talking long enough. See how you do.